Welcome back, Focus Learners. Let's jump right into Section 2, Episode 2.1 of our explainer. Today, we're talking about the relay's eyes and ears, conventional inductive transformers. We're looking at that absolutely critical physical interface between massive electrical switchyards and the sensitive numerical logic of our modern protection relays.
And I want to start with a hard truth. Every fault decision the RE615 ever makes is only as good as the signal it's given. It's really that simple. If you get the current and voltage transformer sizing wrong, well, the smartest protection algorithm in the world is suddenly just reading a totally distorted picture of reality. The relay can literally only protect what it can accurately measure.
So to make sure we're getting those vital signals exactly right, we're going to trace their journey today. We'll hit the relay's eyes and ears, scaling down dangerous power, hardware-agnostic setups, the distance and burden rule, and finally, calculating true accuracy. Let's get into it.
Part 1. The relay's eyes and ears. Think of the RET615 chassis itself as a highly advanced hot-swappable brain. But, like any brain, it's essentially trapped in a dark box. It relies completely on external current and voltage transformers to act as its sensory organs. Without those analog senses, it's completely blind and deaf to the very network it's supposed to be protecting.
Now, because the vast majority of substations out there are still rocking conventional analog current transformers, CTs, and voltage transformers, VTs, our relay has to interface seamlessly with that installed base. That is exactly what an instrument transformer does. It's a device purpose-built to scale down the massive primary currents and voltages from the yard into standardized, safe secondary signals that the relay can actually process. Which brings us to Part 2, scaling down dangerous power. Out in the primary switchyard, you are dealing with incredibly huge, dangerous power. It's intense. That energy has to get physically scaled down by the CTs and VTs into small, safe, readable metrics for the relay's input ports. The physical ratio of the transformer out in the yard is doing all the heavy lifting here, delivering a completely safe secondary output directly to your relay panel. To be specific, the RET615 handles a selectable 1 to 5 amp range for current and a 60 to 210 volt range for voltage inputs. But listen, I have to issue a massive safety warning right here. You must never, ever operate a live CT secondary circuit open, not even for a second. An open CT secondary under load current can develop lethal voltages. We are talking about destroying equipment insulation and causing severe, life-threatening injury, so keep it close. Okay, moving to Part 3, hardware-agnostic, software-defined. A lot of engineers assume that if you have different CT outputs in your yard, like say some are rated for 1 amp and others for 5 amps, you automatically have to order completely different relay hardware for each setup. But thankfully, ABB gave us the 1/5 amp selectable software setting. This one simple software toggle makes the relay hardware totally agnostic to the specific CT secondary rating. It's exactly like a hearing aid. The relay literally adapts its hearing to whatever environment it's placed in. Whether it's being fed by a 2000 to 5 CT or a 2000 to 1 CT, you just toggle a dial in the software. You get to reuse the exact same physical device across completely different projects. That is a massive cost and stocking advantage, because you aren't warehousing a bunch of different spare parts for every single CT rating in your facility. And once that software hearing aid is tuned properly, the data path is incredibly direct. The analog signals flow straight from the physical CTs through the properly scaled input ports directly into the relay's internal protection blocks. But think about it. If you get that software toggle wrong, every single downstream protection block is going to inherit a fundamental mathematical error. All right, Part 4, the distance and burden rule. Let's do a quick check to test your engineering intuition here. Think about the actual physical realities of copper wiring for a second. If you have a really long cable run from your CT way out in the switchyard all the way back to your relay panel, which secondary rating would you prefer to specify? 1 amp or 5 amps? The answer, you'd want to go with a 1 amp secondary rating. Why? Well, it's just physics. Lower current traveling over a long run means lower I²R resistive burden losses in the copper wiring itself. By choosing 1 amp, you easily maintain your measurement accuracy over that long distance. Now, 5 amp CTs are still great, but they are traditionally preferred for shorter runs where those burden losses just don't add up enough to cause problems. And finally, Part 5, calculating true accuracy. The absolute crucial point here is calculating the true safety factor, which we call F'(L).
See, instrument CTs are actually designed to deliberately saturate during a massive short circuit. This is to protect the relay's sensitive input ports. But to know exactly when that saturation is going to happen, we have to separate the CT's rated numbers from its actual real-world loading. We need to find S real, the true load at the CT secondary. And honestly, finding that true load, S real, involves some pretty elegant math. We just take the rated secondary current, square it, and multiply it by the total resistance of the circuit. Now, that total resistance is just the relay's own self-consumption resistance added to the resistance of the copper wiring. Knowing this is critical. It guarantees you aren't accidentally pushing your CT into early saturation just because your cables happen to be too long. But hey, what if you're doing differential protection across a transformer and your switchyard has totally mismatched CT ratios on either side? Well, the relay uses this KNN normalization formula. It looks at the CT ratio of the specific terminal you're dealing with, compares it against the highest CT ratio used in the zone, and factors in the nominal secondary current. This right here is the true power of numerical relays in action. By applying that KNN factor, the relay converts all incoming currents into per-unit values. It mathematically forces an apples-to-apples comparison. It completely levels the playing field, making sure the relay isn't accidentally tricked into tripping just because the physical CTs on the high voltage and low voltage sides happen to be different sizes. Pretty brilliant, right? Okay, let's take a quick breath and summarize this new toolkit of yours. You now know exactly how to specify input settings for your analog signals. You can confidently justify your copper cable run choices based on the physics of burden. And you understand how the relay mathematically normalizes completely disparate signals using software, all to make those accurate split-second protection decisions.
But I want to leave you with one final kind of provocative thought. We've just spent all this time in this explainer optimizing copper wires, calculating their resistance, and dealing with physical transformer ratios. Well, if we can digitize the settings and the math inside the relay, why not just digitize the wires themselves? What actually happens to all these strict rules when the copper cables vanish entirely? That is exactly what we'll answer next time when we dive into the digital process bus. Until then, stay focused and keep learning.